The purpose of this video will help you learn how to draw Lewis structures or Lewis structural formulas for many of the common biological molecules that we're going to see over the course of the year in this class. So as you can see on this screen, biological molecules come in many forms. For example, some molecules like methane are pretty simple. Other molecules like acetylene have triple bonds, while in methane there was only single covalent bonds. Butadiene has both single and double bonds. Some biological molecules actually have ring shapes with alternating single and double covalent bonds, while other molecules like isooctane have a branch structure, where there is a linear chain of carbon and hydrogen atoms with branches that come off of that linear chain. Okay, so this is just to show you that there are different forms of biological molecules. The molecules that you'll be drawing most often won't be quite this complex. I just want to give you a sense of some of the diversity of molecules that exists within the world of biology. So we can draw biological molecules using Lewis structures. And Lewis structures simply are structural formulas that show how atoms in a particular molecule are bonded together. So in the case of carbon dioxide, we can see that we have a central carbon atom bound to two oxygen atoms via two double covalent bonds. In the case of ammonia, we have a central nitrogen atom with three hydrogen bonds bound to the nitrogen. Each of those hydrogens are bound with single covalent bonds, and the same applies to methane, except for this time carbon is the central atom rather than nitrogen. So as you probably know from ninth grade, we can, whenever we draw a single line with a structural formula, that single line is meant to represent a single covalent bond. Well, we want to go a little bit further in this class and make sure that we understand that that single covalent bond represents one shared electron pair between the two atoms that are bound together. If there are two lines, that's a double covalent bond. If there are three lines, that's a triple covalent bond. And in the case of the two lines, remember that that would mean that we have two shared electron pairs. In the case of a triple bond, we have three shared electron pairs. Now there's going to be times where we're going to have to place electrons in our structural formula that are not involved in bonds between atoms. And when that happens, we're going to have to use dots. And those dots will represent the electron pair on that atom. You have to excuse my drawing. It's not perfect, but it will do the trick for now. Later on, we'll actually be building three-dimensional representations of different biological molecules with the modeling kits that we have available in class. Okay, so how are you going to draw a Lewis structure? Well, for this example, I chose the molecule of iodomethane. Now, iodomethane is not a very common biological molecule, but it's a good example of a molecule to start with if you want to learn how to draw Lewis structures correctly. So the first step in drawing a Lewis structure is to make sure that you know how many atoms are found in the molecule. So as we can see here, in the case of iodomethane, we have one carbon atom, three hydrogen atoms, and one iodine atom. Okay? Now we're going to use the number of atoms to figure out how many valence electrons we're going to need to place in our Lewis structure. Now remember, valence electrons are the electrons found in the outermost energy level of a particular atom, and thus those are the electrons that will form or can form chemical bonds with other atoms. So to determine the valence number of electrons, we could actually go out and draw electron configurations, but remember that if we know the group number where the element is found on the periodic table, we also know the number of valence electrons that particular atom will bring to the molecule. So in the case of carbon, carbon is in group 4 and brings 4 valence electrons. Hydrogen is in group 1. Each hydrogen atom brings 1 valence electron. There are 3 of them in this molecule. So that's a total of 3 electrons. And finally, iodine is in group 7. Iodine has 7 valence electrons and will bring those electrons to the molecule. So grand total, in the case of iodomethane, we have 14 valence electrons that will ultimately need to be placed in our Lewis structure. All right, now the next step is going to be to arrange those atoms to form a skeleton structure for the molecule. Now, I'm going to draw this molecule on the next slide in just a second, but what you need to figure out first is which atom will actually serve as the central atom in the molecule. Now, if carbon is present in the molecule, you can assume that carbon is almost always going to be the central atom. If carbon is not present in the molecule, and let's be honest, in biology it's almost always going to be present, then what we're going to do is choose the atom that is the least electronegative. Now, you may not have learned about electronegativity in ninth grade, so for our purposes, electronegativity will simply refer to the atom that is furthest to the left on the periodic table, and that will serve as our central atom if carbon is not present. Okay, so I'm going to switch to a blank slide and begin to draw an example of iodomethane. Okay, so remember, we're trying to draw iodomethane. And we knew that in iodomethane there are going to be, let's see, 4 electrons from carbon, 3 electrons from hydrogen, and 7 electrons for iodine. So a grand total of 14 electrons will have to be placed in our diagram. Since we have carbon in our molecule, carbon will serve as the central atom. So that when you draw these Lewis structures, everything that we have in terms of the atomic constituents of the molecule will need to be attached to carbon. And in chemistry, as you'll see as you become more and more familiar with some of the molecules in science, we're always going to try to arrange the atoms symmetrically around our central atom. Okay? Just like that. Once we arrange our atoms, we can go ahead and connect those atoms together with single covalent bonds. Remember, every single covalent bond represents 2 shared electrons. So by placing 4 single covalent bonds, we've placed 8 electrons in our diagram. So of our 14 that we need to place, we've now placed 8. We have 6 electrons that are left over. So where are they going to go? Well, look at the molecule and decide whether or not the valence shells of each of the atoms in the molecule are filled. In the case of hydrogen, we know that hydrogen wants to have 2 electrons in its outermost shell. Because each of these hydrogen atoms that are attached to the carbon atom are attached via single covalent bonds, we know that each of these single covalent bonds represent 2 shared electrons between the carbon and the hydrogen. Okay? So in the case of hydrogen, we know that hydrogen is happy because it wants to have 2 electrons in its outermost shell, and it does. It has the 1 that it brought to the table, its 1 valence electron, plus each hydrogen is sharing 1 electron with carbon. Okay? So that's great. In the case of carbon, each carbon has formed a single covalent bond with 3 of the hydrogens and the iodine. Since each since each single bond, again, represents 2 shared electrons, there's 2 electrons here, 4, 6, 8 electrons around the carbon. Since that satisfies the octet rule, we know that carbon atom is happy as well. But what about this iodine? This iodine is attached to the carbon via that single covalent bond, and only 2 shared electrons are between the iodine and the carbon. And while the carbon might be happy in this case, that iodine atom is not happy. It only has 2 electrons in its outermost shell. We got to fix that. So how do we fix it? This is where those unshared electron pairs come into play. Since we have 6 electrons left over that need to be placed, if we go back to our iodine atom and we place those 6 electrons around the iodine, then we will have successfully completed the octet for that iodine atom. So remember, we have the 2 shared electrons in the single covalent bond, and now I have 3 unshared pairs of electrons around that iodine atom for a grand total of 8. This would be the correct Lewis structure for iodomethane. There are literally billions of different molecules that you will encounter over the course of your science career. And it would be completely unreasonable to ask you to memorize how to draw every single molecule that exists in nature correctly with that technique that I showed you in the previous slide. However, there will be a list of molecules that I want you to be able to draw correctly with Lewis structures. And this is the list of those molecules. There aren't that many of them, and they're relatively simple molecules, but they're molecules that we're going to see again and again and again throughout this year and subsequently in additional years of biology that you take either in high school or you take in college. Okay, so before I sign off, I thought it might be helpful to draw one more example of a Lewis structure from the list that you saw on the previous slide. So the molecule that I chose to draw is ethanol. Ethanol is the type of alcohol that is found in alcoholic beverages and is produced by yeast via fermentation. I wasn't able to draw subscripts in the text box on this slide, so don't worry about that part. Just focus on the molecular formula here at the top of the screen. So we have CH3, CH2, OH. So let's figure out the number and types of atoms that we have present in the molecule. So we can see that we have 2 carbon atoms. One second here, let me switch over. We have 2 carbon atoms. Okay, so it looks like we have the 2 carbon atoms, and then we have 6 hydrogen atoms, and then the 1 oxygen atom. All right, so how many valence electrons will each of these atoms contribute to the Lewis structure for ethanol? Well, remember, carbon's in group of 4, and if there's 2 carbon atoms, that's going to be a total of 8 electrons. Hydrogen is in group 1, 6 hydrogens, so that's going to be 6 valence electrons. Sorry, let me erase that. So that's, again, 6 valence electrons for hydrogen total, and then oxygen is in group 6, so that's also another 6 electrons. So it looks like that's going to be 6 plus 6 plus 8 is going to be 20 electrons total that we're going to need to place in our diagram. All right, so I moved to a new slide, so I had a little bit more space. Let's go ahead and draw the Lewis structure for ethanol. Okay, so we have carbon atoms, and carbon can serve as the central atoms for our molecules. Let's go ahead and draw them in first. Okay, and now we have, let's see, we had 6 hydrogens and the 1 oxygen atom. So what I'm going to do is go ahead and arrange those atoms around this chain of carbon atoms so that it's as symmetrical as it possibly can be. Okay, so there's 5 of them. Remember, I still need to place the oxygen atom. Let's go ahead and do that. And then I'm going to go ahead and place the hydrogen atom next to the oxygen atom. Okay, and we'll talk about why that's going to be the case in just a second. Right, remember, connect all of the atoms in your molecule with single covalent bonds. So let's see, we've placed 2, 4, 6, 8, 10, 12, 14, 16 electrons total in our diagram. Remember how many were left over? Right. We had 20 electrons that were present overall, or needed to be placed in our molecule overall, so we have 4 electrons that still need to be placed in our diagram. So where do they go? Well, again, look and see whether or not all the atoms in the molecule are happy. We can see that all the hydrogens are happy because they have their single covalent bonds and their 2 shared electrons. We know that each of the carbon atoms are happy. Again, 2, 4, 6, 8 shared electrons around each one of the carbons. Okay? This hydrogen atom also is happy because of its single covalent bond with its 2 shared electron pairs. Excuse me, 2 shared electrons, not 2 shared electron pairs. But what about this oxygen atom? We can say that each of these single covalent bonds contributes 2 shared electrons to that oxygen atom. But how many electrons does oxygen want? Remember, octet rule, octet rule, octet rule. This oxygen atom wants to have 8 electrons, and as of right now, it only has 4 electrons around its structure. So what do? We go ahead and place those unshared electron pairs around the atom, just like that. We've placed all 20 electrons, because again, we had 4 electrons that we needed to place, and we just place those 4 electrons using the 2 unshared electron pairs. This would be the correct structure for ethanol. You'll have to excuse its neatness. I drew it on an iPad, but you get the idea. This is what I would expect you to be able to do for any of the structures that you saw on the previous slide, including that for ethanol. All right, so I encourage you to practice with as many different molecules that you can think of, and I'll give you some examples on the next few slides. The more you practice, the more you will feel comfortable drawing these structures. Your goal is to be able to draw the 10 structures that were on the previous slide correctly. But again, the more you practice, the better you're going to be at this, and I think you will find it a useful skill to develop as you continue your science education here at Central High. Thanks for listening, and I look forward to seeing you again in class later this week.